So, we are discussing how we can design the combinational problems or complex combinational problems using fundamental circuits like decoder, multiplexer, adders, etc. Last day we have discussed how we can design combinational circuits using multiplexer, the generalization of that design. Today we will see some large problem design, but before that we continue some the 4 variable design that we are discussing in the last class. So, 4 variable design using muxes. Last day what we have seen that in general a 2 to the power I to 1 mux where I less than n minus 1 can be used to implement an n variable function. So, that n variable is 0 to n minus 1 by choosing any I variables, means that if I have a function f n, say n number of variables a 0, a 1 up to a n minus 1, then first what we have discussed that a multiplexer where that n number of select lines can be used to realize this function. Then always it is possible to design this function using multiplexer. Now, if I want to optimize or minimize the circuit design, then even the lesser number of select lines can also realize the same function. That means that f of a 0, a 1 up to say a n minus 2 instead of n minus 1, that means that n minus 1 number of select lines can also be used. Now, in this case that some extra logic gates may be required. So, today we want to discuss that how we can design using lesser number of select lines with the extra gates at the primary input. Now, first we define the problem. So, this is my design using lesser number of variables, or these variables means we can tell that select lines. So, first say a 0 to a I minus 1 means that I number of lines select lines are used, which determines this I minus number of, which determines the some number k. That means which select lines I want to choose. So, if it is I number, we know that maximum number can be represented by 2 to the power I minus 1. So, that is why my k bound or k is 0 less than k less than 2 to the power I minus 1. Now, the function that I want to realize, that f should be some function of this a I or function of a I. So, that means that f equal to some combinations of a's, that means the select lines, it is ANDed with the some g function that is applied to the primary inputs. That means Gk is a function of ai to an minus 1. If I take a small example, what I can tell, say I am taking a 4 variable, I want to realize say a 4 variable function a, b, c, d. Now, what I can do, among these 4 variables, I will take 3 variables, that a, b, c as the select lines. So, my number of select lines are 3. So, number of select lines are 3. That means, I can be 0, 1, 2, 0 to n minus 1. So, this is here n equal to 3 and this is 0 to n minus 1 means 0, 1, 2. So, these are my select lines. Now, the d is left because I want to realize a function f. So, this d, and as this is a 3 input multiplexer. So, there can be 2 to the power 3, that means if it is n minus 1, that means 0 to say this is 2 to the power n minus 1, these many number of primary inputs can be there, and these inputs can take the value the d, d bar, because d variable is left, and 0 and 1. So, any combination of these d, d bar 0, 1 that should be applied to the primary input, and then it will be passed to that output z, and then it is realized. So, this Gk is a function of n minus 1 to ai. Why this is ANDed? See, this is that any combination of a0 to ai minus 1, and it is ANDed. See that what we have done, that if I take say a0, now say I am telling a0 to a n minus 1. Now, it should take all possible combination, that means a0, a1 up to a n minus 1. So, these will take all 0, then 0 0 0 1, 0 0 0 1 0, say this is a n minus 2. So, this type of all combinations it will be taking. Now, what do we mean by this combination? When it is, when a0 to n minus 1, they are taking all zeros, that means this represents the first combination is actually the complemented of all the variables a0 bar, a1 bar, a2 bar dot dot up to a n minus 1. Similarly, then all complemented 1 means all complemented except the last bit a n minus 1, or reverse also we can take. If we think that a0 is my LSB, then it will be the reverse thing. Similarly, it should take a0, a1, a2 up to n minus 1, means these are all 2 to the power, this is n. So, 2 to the power n 2 to the power n such combinations, if it is 0 to n minus 1. If I take these are n minus 1 variables, then this should be 2 to the power n minus 1 combinations. So, these combinations are applied to the, or these will be treated as the select lines. Now, see here I am taking a function, say some gk values I am taking. So, that for one fixed combination of a0 to n minus 1, that one particular input is passed to the output. Say this is my G0, then for the first combination, when all the variables are complemented a0, a1 bar up to an minus 1 bar, then for this combination, say this is true and then G0 is also true, this will be my output. Now, what is G0? Again the G is the combination of these variables that applied, or function that applied in the select lines. So, it should be ANDed, that means my output should be treated as one particular line or the function applied to one particular primary input ANDed with the that combination applied to the select lines or the according select lines. So, this is a always this will be a AND functions, and there are, if it is n number of select lines, then 2 to the power n such primary inputs or functions available at the primary input lines. So, so far what we have discussed, that means if I summarize that a0 to ai minus 1, that means I number of select lines I have chosen. Now, each primary input, say primary input function is represented as G, then each G or each primary input line can be represented as the function of one particular combination applied in the select lines. That means, say an minus 1 to ai plus 1. I am representing the primary input functions at each line by G. So, there will be, as there are I select lines and this is a mux. So, there are I select lines 2 to the power I number of primary inputs. So, 2 to the power I means this will be 0, this will be written as G0 to G2 to the power I minus 1. This should be I number of primary inputs. So, this we have written as, this is Z0, say the next line would be I1, that will be G1, then this is last line is G2 to the power I minus 1. Now, choose I in such a way so that the total number of logic gates needed for the GKs is minimum. So, today we want to concentrate that how we can reduce this number of select lines. So, that will minimize my design. Last lecture we have discussed the design, that if I take that all the variables as the select lines, then always it is possible to implement or to realize the combination circuit using multiplexer. Now, today we want to discuss that part. Now, first we take a combinational circuit, we take on example. So, this is one example of 4 variable combinational logic design using multiplexer, using mux. Now, that we take the function as a bar, b bar, c bar, d bar, a bar, c d bar plus a bar b c plus a b bar c bar. Now, I can rewrite the function as, see, this is a 4 variable function. First, I am taking AC, the 2 variables as the A and C are the select lines. So, these are my A and C are my select lines. So, if AC is the select line, then this should be a 4 to 1 mux, because if there are 2 select lines, that means 2 square or 4 number of primary inputs will be there. So, this is the 4 number of primary inputs and 1 primary, 1 output. So, the variable left are B and D. I have taken AC as the select lines. So, AC should take that, say if it is AC are the select lines. So, if A and C are select lines, then the combinations the AC can take AC combinations that the select lines can take, or we can think these as the control inputs. Are 0 0 0 1 1 0 1 1. See, 0 0 means A complement C complement, this is A complement C, 1 0 means A C complement, 1 1 means AC. So, now I want to represent this function with respect to this A bar C bar, A bar C, AC bar, AC. Okay. The first min term A bar B bar C bar D bar. So, if I take A bar C bar common, then B bar D bar is left. So, the first min term is written as if A bar C bar ANDed with B bar D bar, plus here the second term is A bar C and D bar. See, another, the fourth min term is also AC, or third min term is A bar C. So, this is D bar plus B. If I take common, then A bar C ANDed with D bar plus B. This is AC bar, only B bar is there, and see, there is no term consisting of AC. So, that is why I have kept AC ANDed with 0. That means, this term does not exist in the function. So, now if I consider a multiplexer design whose AC value can take these variables, that means my I0 input can, this is my I0. So, this I0 can take see, I0 means A bar C bar. So, this should be B bar D bar. See, B bar ANDed with D bar, that means the first primary input is B bar D bar. I am assuming that the all complemented variables are available. So, this output of AND is the B bar D bar. Now, if I consider the second primary inputs means I1. Now, second input means the select line should be 0 1 means A bar C. So, the select line should be A bar C and then I1 should be passed to F. Then what is my I1? From the function we see I1 is D bar plus B. So, this is my A bar C and this is my D bar plus B. So, this is my I1 term. So, second input, so again this is D bar and this B and this should be OR. So, this OR output is D bar plus B. Now, we see that the I2 line. So, I2 primary input is the AC bar. Now, see AC bar means that it is my B bar only, it should be ANDed with B bar. So, this it is ANDed with B bar. Now, I3 is that 0 because this term was not there in the function. So, this is I3. So, the I3 is 0. So, this is one multiplexer realization of this function where we have taken 2 variables as the select line instead of 4 variable, but some extra logics we have applied in the primary input. So, this is one optimal design of this particular function. Now, we see that we discuss the last is quiz question. So, quiz question was that realize the following 4 variable function using multiplexers. The function was z equal to a bar b bar c d bar, a b bar c d bar, a bar b bar c bar d bar, a b bar c d bar plus a b c d. So, just now what problem we have discussed, it is a similar type of function. See what will be the answer. So, again what we will be doing? First we will rewrite the function in terms of the select lines. So, first we have to select that what will be the, what variable we will be taking as the select lines. See here the number of variables are are 4. They are A, B, C, D. Say among these 4 variables, say AC, just like the previous example, AC are considered as select lines. So, what I want? I want a multiplexer design whose select lines are AC. As there are 2 select lines, so obviously there will be 4 primary inputs. They are I0, I1, I2 I 3. There will be one primary output Z. Now, we see that AC can take again my select lines can be A bar C bar means 0 0, A bar C means 0 1, A C bar 1 0, A C 1 1. So, my next step is that I want to make or I want to design that function as the AND function of this combination of select lines and that particular primary input, so that it realizes each min term. So, we see the min terms first. So, min term is A B bar C bar D bar. Among these 4 variables, AC are the select lines. So, with AC here this min term AC exists in the form of A bar C. So, this is my that actually it should come to the I 1. So, I am giving this is my I 1 term where it is A bar C into B bar D bar. That means, A bar C ANDed with B bar D bar, this gives my I 1, this gives my I 1. Next term consists of A bar C bar, and the third min term, that means the second min term and the third min term both consists of A bar C bar. So, my first primary input I 0 should be A bar C bar B D ANDed with B D plus B bar D bar. So, this is my I 0. Similarly, the AC term, there are 2 min terms, the 4th and 5th min term consist AC. So, from here and here if I take AC, then again it should be also B D plus B bar D bar. This is my actually I 4 term, I 3 term. This is my I 3 and this is AC bar. There is no AC bar exist in the function, that means there is no min term where AC bar is there. So, this is my I 2, this is my I 2. So, now the first I 0 term consists B D plus B bar D bar. So, if I first it should be a OR. So, this should be a output of OR whose inputs are B D and B bar D bar. Again what I can do, this can be 2 on AND function whose 2 input are B, D and B complement, D complement. Now, this B D plus B bar D bar, again that is the function of the I 3 term. So, directly what I can tell, that the same output I can give to I 3. This is my I 3. And the I 1 and I 2, these are different. So, I 1 is A bar C into B bar D bar. I 1 is simple B bar D bar, that means one AND function, 2 input, this is B bar, this is D bar, and I3 is I2 component is 0, this I2 is 0. So, it will realize the same function what is given. Now, there can be another realization. See, this actually BD plus B bar D bar, this is nothing but a realization of the XNOR. So, this is a XNOR, 2 input XNOR whose inputs are B and D, then this is actually BD plus B bar D bar. So, what we can do, that input of I0 and I3 can be replaced by a 2 input XNOR. So, if I again draw that, these will be my 2 select lines AC, that I0 and I3 both are coming from some XOR XNOR output. The outputs are, both the cases outputs are BD. So, both the cases, that 2 input it is BD and this is a BD plus BD bar, and I2 was 0 and I1 was B bar D bar. So, it will be as it is, I1 and I2 is 0. So, I2 is simply made 0, I1 is again 1 2 input AND whose inputs are B bar D bar. So, these inputs are. So, again this can be another realization where, so this is my, this is a 4 to 1 marks, and actually this realizes the function given, realization of the function Z A B C D. So, in this way we can get a optimum marks realization, optimum design using multiplexers. Now, another thing is that even we can, so we have to select a appropriate number of or minimum number of select lines, and based on that the input lines to be designed. So, some extra logic circuits, so these are my extra logic circuits are needed, or we can tell the extra gates that are needed to realize the function. Okay. So, now we shift to a different type of design problem. Again, that is a combinational problems, combinational logic design. This is a interfacing keypad with LED display and bus. So, first we see that what is the problem. So, we want to design a interface. This is the interface design problem, and see there are and I want, this is a LED, that 7 segment display. Here there are 7 components, say A, B, C, D, E, F, G, and we want that every segments to be, every segments are the output of one design. That means the outputs are, say if I take the outputs, these are A, B, C, D, these are the 7 segments, and parallelly I want that this should be, taken, this should go to the bus also. Now, these are the, if I want that all the digits, we know that here, see that if I want to draw that 0 or 0 to display, then I have to, that 6 segments, among the 7 segments, that except G, all the 6 segments should be accepted. Similarly, that for 1, that either FE or BC, that 2 segments should be selected. Similarly, all these segments should be. So, this is my problem design, that I want some inputs and which will give the, which will select the control lines, so that it can, again it can select the particular segments for a digit. So, this is the problem. So, overall thing, so this is a BCD to 7 segment control signal decoder. So, here I want that these ABCD are my inputs. So, this is a problem, or this is a combinational circuit design where the inputs are A, B, C, D and outputs are that the 7 segments ABCD, ABCDs, EFG, the 7 segments. So, this is a BCD to 7 segment control signal decoder. We can represent this problem like that. Now, first thing is there are 7 output lines. Even if we ignore the other control signals, that for each segment will be treated as the output lines. So, there are the problem now, problem becomes that as if there are 4 input lines ABCD and that 7 output lines, that the output lines are as if that all segments ABCD EFG. So, if we consider, so these are the Carnot maps that for that each segment. So, if we consider that Carnot map for D, any one we can take, this is a Carnot map for D. I have 4 variables. So, this is A, B, C, D. So, see that A bar, B bar, C bar, D bar, this should be true, or this min term will be there. Similarly, that here A bar B, C bar D, that is also there. So, this one, this is one, this one, there will be. So, now from that Carnot map concept, what we can do? We can reduce the or we can minimize the function. First, we will select that couple as already we discussed, and similarly for each segment, that this is for my A, this is for my Carnot map for B, C, D, E, F and that G. This is for G. We can first we will draw the Carnot maps for each segment, as if this segment is the output for the design. Then the control input expression, because these are nothing but the control segment, that which segment should be selected to give a particular digit. So, for A is that if I minimize the function using Carnot maps, then A is A plus B D plus C plus B complement D complement. Similarly, B is A plus C complement D complement plus C D plus B complement. C is similarly A plus B plus C complement plus D. So, mainly what we got, we have say 7 we can tell that output expressions. Now, how we will design this thing? These are my expressions. Now, how we will design? Now, there can be many designs, because these are nothing but some 7 combinational logics, several. Now, as this is a large set of expressions, what we can do? There can be different type of realization, or what we can tell that different implementation style. One, first what we can do, the simplest one is the design implementation using gates. See, if we again notice that for A, this is nothing but AND OR expression. So, this is A plus B D plus C plus B complement D complement. So, I can write A equal to A plus B D plus C plus B complement D complement. How I can do that thing? Again, that there are 4 inputs. So, simple this thing I can do, that this is a 4 input OR, A, then C, then B D and B complement D complement, which is nothing but a, I can, if it is a 4 input XOR, then this is one AND whose two inputs are B and D. The fourth one again it is a AND whose this is a B complement and this is a D complement. So, this is one simple realization I can do. What I can do, this another realization can be again if I consider A equal to A plus BD plus C plus B complement D complement. So, if it is not a AND OR gate, any using any other logic gates, if I want to minimize the gates and say I have all or a different type of gates are available, I have that option that AND or XOR, XNOR, whatever that all possible gates that are available. It is not a AND OR realization. Then what I can do? Again I can take that this is a 4 input OR and say simple A and D or A and C are fed as it is. Then see BD and B complement D complement is nothing but a XNOR. This is a XNOR output whose inputs are B and T. So, this can be another realization of A. So, similarly, if we see that other expressions, see this is A plus C complement D complement C D plus B complement. See that these are very similar, that C D plus C complement D complement means this is C D plus C complement D complement means again this is nothing but a XNOR realization whose inputs are C D and that A and B complement as it is. So, this is a similar type of structure. So, in this way I can design this 8 expressions for or that 7 segments, 7 expressions using that simple combinational logic or simple logic gates. These are nothing but the combinational logic designs. Now, only thing is that this should be a this should be a ABCD. Say if I take this as this design as the black box, then there will be 4 input, that A, B, C, D. The segments are A, B, C, D, E, F, G, and just now what we have discussed, that say this is my logic design of A, say one, this is one 4 input OR gate where this A is there, C is there and the that XNOR if we consider, or BD and BD bar. Okay. See if it is simple, this is B and BD bar, this is B and B bar D bar. So, this similarly for all segments there can be the different type of circuitry and we can put in this way. Now, say I can tell that there can be many other design structure. So, this is one type of thing. This is design using gates. Now, the second style can be that this can be a design using the ROM. So far we have not read the memory design. So, using the read only memory we can also design this thing. This can be designed using some programmable array logic, it is called PAL or PLA, programmable logic array, or some CAT tool. If it is a big design, even some CAT tool can also synthesize or realize this function in different way. But normally the CAT tool will be using any one of the three. That means CAT tool will use either 1, 2 or 3, these options. So, these are the different styles. So far we have read only the design style or the implementation style of one, that means the combinational logic gates. Now, another thing is that combinational logic design that just now we discussed using simple AND OR logic or the XNOR, that also if it is a big design, that also we can do using multiplexers, using decoder, or if it is a different type, actually depends on application, it can be using adders, half adders or full adders. So, when we will be reading that the memory, read only memory and the programmable logic arrays, then we will discuss that how the combinational logic can be designed or the complex combinational logic can be designed using these ROM or PAL and PLA. Now, our problem was, our design problem was the interfacing keypad with LED display and bus. So, see if this is my keypad, say I have 15 such keyboard. I want that when I press one key, say that number 5 key, then that binary should be, that should be, or in that display board that 5 will be activated. And for that I have to, for that particular segments of the 7 segment display must be selected. So, you see that what will be the, so if I take that, this RC means these are rows and columns. So, these are the, there are 4 row and 4 columns. So, this should be here, this should, for 5 it should be the second row and second column 2 2. So, similarly for 10 it should be third row third column, like that. So, these are RC gives the all the elements or the all the keys, the position of all the keys. It should be 1 1, 1 2, 1 3, 1 4, means this is my first row. Similarly, if it is, this can be second row, third row, like that. Now, the bus lines, this is my bus lines. That means, when this 1 1 should be pressed or 1 2, that then this bus lines should be 0 0 0 1. This is some 4 bit lines we have given, because I have 15 such keys. So, I need 4 bit to be. Similarly, this is for my most significant driver lines, and this is the least significant driver lines. So, now if I, similarly if I design the Carnot maps for every line, then I will be getting the circuit in similar manner. Now, using decoder and multiplexer, I can design the circuits. This is my overall design. Say I have used a 4 to 16 decoder. Okay. So, these are my ABCD lines, these are my 4 inputs, and I have used 4 2 to 1 multiplexer, which are actually driving the least significant late driver and the most significant late drivers, the 4 bits, and accordingly the late are displayed. That means that particular segments of the lead are selected and they are displaced. So, this is the overall circuitry. Now, that lecture 18 quiz. So, design a 4-bit barrel shifter using multiplexer. This is the next test thing. Thank you. In the last few lectures, we have learned how the combinational circuits can be designed using functional blocks or the fundamental circuits like decoder, multiplexer, adders, etc. Lastly, we have seen some generalized structure of realizing combinational circuits using multiplexer. Now, today we will read another type of combinational logic design using programmable arrays of logic gates. But before that, before we start that programmable arrays, quickly we solve the last day's quiz question. The question was that a design, it is a 4-bit barrel shifter using multiplexer. So, answer we see that already we have discussed the 4 to 1 multiplexer design. It has 2 select lines and 4 input lines, 1 output lines, and this is the IEEE symbol for 4 to 1 multiplexer. We will use this multiplexer to design a shifter, 4-bit shifter. Now, first we see the normal combinational logic shifter. See, this is 4 to 1 multiplexer we have used. This is my mux 1, mux 2, mux 3, mux 4, or reversely we can take that outputs are S1, S2, S3, S4, and the functions that F1, F2, F3, F4 that we want to implement or we want to pass that thing as the output. Now, there are the shifter